Welcome back to STEM Talk with STEMencounters, episode number 3. I'm the CEO and founder of STEMencounters, as well as the host of STEM Talk with STEMencounters, Saif Panjwani. So, for new listeners who don't know, we run a student-led 501c3 nonprofit known as STEMencounters, dedicated to teaching, expanding, encouraging STEM knowledge for everyone. So, if you want to know more about us, go to STEMencounters.com. We have online courses, event planning, blog posts, information about STEM, and new updates almost every day. Today, we have a special podcast. We have guest Dr. Yang, material science and engineering professor from Columbia University. So, without further ado, let's just get into the STEM. So today with me on STEM Talk with STEMencounters, we have a very special guest, Dr. Yang, an associate professor of material science and engineering in the Department of Applied Physics and Applied Mathematics at Columbia University. Thank you so much for coming on this podcast, Dr. Yang.
Yeah, my pleasure.
So give me some generalities, go in depth on what you do.
Okay, so as Steve said, so I'm an associate professor at Columbia University in material science. So I work on developing new materials for energy applications like batteries or like coatings for buildings to save building energy.
Okay.
Yeah.
That's very cool. So tell me a little about your background. Where did you go to college and why did you choose that college?
Okay. I went to Peking University in China. So and my major in college was physics. So Peking University is one of the two best universities in China. So because I was born in China, that's why I decided to go there. And the reason physics as a major is that I like physics a lot. Yeah. So that I want to learn science. So that's why I choose physics as the major. Yeah.
And physics is also very important for material science and engineering. So
yes. So for high school, so let's say the material science as a combination of physics and chemistry. We study physical and chemical properties of different materials like metals, plastics, and many other things.
Yeah. So what made you eventually pick the field of M.S.E, come to America and pick that field? And why do you think it's so important?
Okay. So in college, I also find that I also like chemistry. Okay, so physics and chemistry, and I like to understand the how materials work. So I think material science is a good choice. And so when I apply for PhD in United States, half of my application went to physics and half went to material science. So the Stanford material science was the best offer I got, so that I decided to choose material science. Okay, and after I joined Stanford, so the topic my PhD advisor assigned to me is on batteries. So and that's why I start to work in the field of energy storage and broadly energy materials, and I feel it's very exciting. So it's really happy. I mean, the goal is to solve the problems that the human is facing. So I feel very excited about it.
Yeah, it's while reading your research, I was very interested. So as you said, you researched batteries and energy. What made you pick these topics when researching when you came over here and eventually got your PhD?
Okay, at the beginning, so like the battery, so that's the I mean, that was a topic picked by my advisor. Okay, I didn't pick it up by myself, but by my advisor. And after like 1 year on this topic, I feel that I'm really interested. I'm interested in how to make battery last longer, so that can be charged faster. So I want to have solved the problems in batteries. So that's why I continue on this path.
Yeah, it was very interesting. Especially, I was looking online and I saw some of your YouTube videos on flexible batteries, and then how it could be twisted, and the smartwatch was actually still charging. So, how did you go about doing that? How did first of all, can you explain the research behind it, and how did you go and making that whole smartwatch charging flexible battery?
Okay. So basically for battery studies, so one direction is to like, for example, enhance the performance. So
Yeah.
for example, to make it last longer and can be charged faster. So that's definitely very, very important. And those are like big challenges. So another direction is to think about so what new features or like what new capability can battery have. And that's also my interest. So that's why I work on is like the battery and the flexible batteries. So because I want to accommodate battery to some
Yeah.
special scenarios and to make the battery useful in applications as wide as possible. So and the flexible batteries, say one example. Um, so so the typical design for flexible batteries is to use some flexible materials inside, like some people use carbon nanotube, some people use like a plastic. Uh, the challenge is that so those materials don't have performance comparable to the materials used in state-of-the-art lithium-ion batteries, like the lithium cobalt oxide or the graphite. So, but when you use the battery, so the how much energy are inside, that's the number one consideration. So, for example, if a battery is flexible, but it only lasts like a half as long as a normal battery, you won't be attracted by the flexibility. Okay, so you need to try to keep the energy stored inside at the same level as conventional battery, and then add the flexibility or transparency function inside. Okay, so that's my philosophy on like how to design the flexible battery. So I decided to say, okay, so I need to keep the energy to be roughly the same as conventional batteries. Then what to do? Okay, then I try to think about, so then you need to use traditional materials. And then it's different. So if we cannot some new or fancy materials, then maybe we can change the structure of the batteries. That's how I get the idea to
Oh,
make this like you can call it bamboo like, I'll say like the spine like
yeah.
structure to make battery flexible.
Yeah.
Mhm.
Just a question, is that the research behind that? Was that the paper that you wrote? Was that the paper you were most proud of? Like,
I think that's not the one I'm proud of. So I like my the science paper on the radiative cooling most. Okay,
oh,
so that's like another application. It's not about batteries.
mhm,
Uh, So the radiative cooling is a new cool concept. I mean, it's old, but like recently, have made some really exciting progress. So it's basically, uh, so if you have something like a very reflective in sunlight, so like for example, if it's 100%, I mean, it can reflect 100% of sunlight, then even if I mean, even if it's placed on the sun, so the surface will not be heated by the sun. And people also know that the sky is much colder than the surface of Earth. So it's 50 degrees Celsius cooler than the Earth's surface. So then heat can also move from a hot to a cold one by the so-called radiation.
yeah,
Basically, I mean, if you are sort of far away from the fire, you can still the heat. So that's basically the heat is reached you by the thermal radiation.
mhm,
Okay. Uh, so in this way, so if you have, but the radiation is in the wavelength of like say 10 micrometers. So that's much longer than the uh, light in the solar spectrum. So then if you can have a surface that's fully reflective in the sunlight, but can also emit heat to the cold sky, then the temperature of the surface will be cooler than the environment.
Oh, okay.
Okay, so basically because it's not heated by anything, but it also loses energy to the cold star.
Oh, okay.
Okay, so then that's actually then because it's losing energy, so that the temperature will drop.
Oh, yeah, that sounds like a very interesting paper.
Yeah. So basically, people achieve, say, the temperature lower than the environment. So first in 2014. So under very strong sunlight. Okay, that means at noon. So the surface, the temperature will still be lower than the environment.
Mhm.
Okay, and in 2018, we developed a cheaper approach to apply such to achieve similar capability, but the cost is much lower. Okay, so it's that we develop a new kind of paint, so we can directly brush it onto the wall of buildings, and then the whole building can keep very cool. Yeah.
Oh,
Mhm.
okay. Yeah, that is a very, very interesting paper.
Mhm.
So, going along to something on your Columbia description. So it says on your description on Columbia University site that you design, characterize, and analyze materials and devices for electrochemical energy storage and conversion, for example, like batteries, like you said,
Mhm.
water splitting, and thermal management, for example, like the solar absorber.
Mhm.
So, you told me a little bit about why you do this, but and why you got into it. But why do you focus on this rather than other topics in MSE to this day?
I think one reason is that I like to work in the field of energy because energy is like a very important topic, a very important topic, and it helps us to address the environmental and also CO2 emission, climate change, lots of important
Yeah,
challenges. So and you know uh, I'm also interested in many other topics like 2D materials like the semiconductor. So if you want to make impacts, so you need to focus. Okay,
yeah,
you need to work on something. Uh, I mean, focus on one thing instead of many
yeah,
things. Yeah.
yeah, yeah. That's definitely right. You need to put all yourself into one's field, and energy is definitely something that we need help on, and it's because of like your work that we can actually improve for the future. So it says you have used synchrotron, TEM, transmission electron microscopy, and optical approaches to understand various electrochemical reactions, such as growth of
Mhm.
lithium dendrite and the dissolution of polysulfides. So can you tell us what that is, what it can be used for, and why it is important?
Okay, so battery is actually like a black box.
Yeah.
Right? So we know that it can deliver charge,
Hmm.
but we don't know how things work inside. So
Hmm.
if you don't know how things work inside,
Hmm.
then you really cannot fully understand it.
Yeah.
Okay, so you need to really see what's inside to in order to understand it.
Hmm.
And so the X-ray is like a powerful, uh, say, a powerful light, so that can penetrate the batteries.
Hmm.
Okay, so that the visible light cannot penetrate batteries, but X-ray can do the job. Actually, so we use X-ray to do CT for our human
Oh,
body. So you can consider the synchrotron, so which is a kind of X-ray. So it's like to do a CT for batteries. So we can how the charging and the discharging of batteries affect the size, the dimension
mhm,
uh, of materials inside the battery.
mhm.
Okay, so the good understanding inside will be able to design better batteries.
Okay.
Okay, so that's like a fundamental understanding of the mechanism of battery charging and discharging to help us to design better batteries.
Oh,
Mhm.
okay. Okay. So yeah, that's very, very interesting. So moving a little on to what your background. So you won many awards, including the 2019 Young Innovator Award by Nano Research and the 2019 Emerging Investigator by Journal of Materials Chemistry. So is there any award you are most proud of, and what research in material science and engineering allowed you to get the award that you were most proud of?
The most, I mean, the award I'm most proud of
Mhm.
is the uh, actually the MRS postdoc award.
Okay.
So MRS is short for the Material Research Society.
Okay.
It was awarded to like I think 4 postdocs per year. So in the Material Science Society. Okay, and so it's really, I would say, the highest honor for postdoc in material science.
Wow.
Okay, yeah. So I won it, I think, in 2015.
Oh,
Yeah. So and so yeah, I was honored, and it's I mean, um, so the award was based on my postdoc research. So it's actually to combine batteries with thermal management. So actually it's a way to use batteries to convert the heat to electricity.
oh,
Okay,
okay.
so it's just actually something, and we develop some new materials that can increase the efficiency for this heat to electricity conversion.
Wow.
Mhm.
That's incredible. Yeah, that's definitely something that I would be proud of as well. Uh, so when reading your research, something that interested me was your publication on bioinspired spine-like flexible rechargeable lithium-ion batteries, like we talked about, with high energy density. It was really fascinating how you put your work on high performance flexible batteries with animal vertebrae to create more efficient and more fully functional batteries. In fact, the video I talked about before, where there was a little graph, it was testing, it was going up and down like this and this, and then the graph was going up. So you told us a little about that, but if you remember that video, can you tell us what the graph represented, a little bit about that, and then, yeah, what did that graph represent? And for anyone who doesn't know what I'm talking about while watching this, I'll put a video up really quickly. So, do you remember what that was?
You mean something like the battery is like this shape, and then like a stretching, and then
Yeah.
pushing back. Okay, so that's actually a video just to show the battery is flexible. So the
Okay.
pushing back is like to make it. I mean, the pushing back is like to bend it.
Mhm.
Oh, okay. Then it's just to show that I can after many times of bending, then performance is the same.
Oh, okay. And
Mhm.
then the graph behind it was just that it was actually working, like showing proof.
The drive behind actually the voltage
Okay.
curve of the battery. Okay, so for example, if like the common rigid battery, if you bend it, so the battery will be broken. So I mean, it will break, so that the battery voltage will go to almost zero. So that means the battery cannot discharge any current.
Oh.
Okay, but now you show that the voltage is very stable.
Mhm.
Yeah. Mhm.
Oh, okay. Yeah, I saw it was working, and that's what I was thinking, but yeah, I just wanted to be sure. So, is there any publication that you're currently working on? I know this is we're in a time of uncertainty during this pandemic, but is there any publication that you're currently doing or thinking about in material science and engineering? And why do you want?
I, yeah, I'm still continuing on the battery and the thermal
Okay.
management research. So due to the COVID-19, so I'm mainly focusing on simulation work. So like to use some tools. I mean the modeling softwares to understand
Mhm.
so how ions move in the uh, batteries and how to improve the performance of the coating I just mentioned.
Oh, okay. So, uh, could you just say one more time, what are the benefits of these batteries? Just so if anyone missed it.
The flexible battery or what? Like in general?
Yeah, the flexible battery, and then in general for the future.
Okay. The flexible battery is I mean, the advantage is that if in the future, if you have a flexible electronics, like okay, one simple example is that in the Apple iWatch, so if
Okay.
you can replace the watch belt with flexible battery, then actually can make the operation time to be twice or three times longer. Okay, I mean, if you don't want to increase the operation time, also remove the battery inside so that the display panel will be like much thinner. Okay.
Oh, okay. So just yeah, increasing time overall. Yeah. So yeah, that's a very, very good application for anyone who uses Apple Watches and all that. So in the world of material science and engineering, do you have interest in material science and engineering integrated with new forms of technology like artificial intelligence? So
We are working on it. So uh, there actually have been some exciting progress combining artificial intelligence and battery studies. I mean, not by myself, but by other groups in the field. For example, there's a group from Stanford, so they can, based on the first 10 or first 100 cycles of batteries, then predict the performance after 1,000 cycles. Okay, and that's from the artificial intelligence. Okay, and also they use artificial intelligence to figure out how, uh, so what's the best way to charge a battery. So for example, if you, okay, so say we charge the battery in 10 minutes. Okay, then but after in the 10 minutes, the current doesn't need to be a constant. Okay, and then there's actually one protocol that can enable you to, uh, the charging time is 10 minutes, but the battery capacity retention is highest after, say, for example, 100 or 1,000 cycles. Okay, and that will be very helpful. Yeah, so that's some progress on integrating artificial intelligence and battery these days.
Wow, yeah, that's really cool. So something that actually we covered, we had a recent blog post on artificial intelligence and material science and engineering, and it talked about how we can use machine learning to identify fractures in materials much quicker. So, like for example, engineers don't have to like strain their time and energy over picking the right materials for a project. So, from a professional standpoint, what could this mean for the future? And do you have any like comments on this?
Uh, I, I, I'm not aware of this work, but I do see. I, I'm, I mean, I have no doubt on that. I think machine learning do help uh, us a lot to in order to speed up.
Yeah.
One challenge for combining material science and machine learning is that material science is a discipline that with small data. So I mean, at least it's not easy to have a large amount of data, and that's actually one challenge to combine with artificial intelligence and new methods to speed up the accumulation of data is very important for this direction. And I'm sure machine learning can help us a lot in order to find new materials and new solutions to existing questions.
Yeah, yeah. That I actually didn't even know that that's one of the drawbacks. So that's very interesting to learn. So, is there any astounding research in material science and engineering that you've read recently and you think is revolutionary? And why do you think so?
I think. Um, so one thing in my mind is like the development of aqueous battery. So like recently the people actually come. I mean, so the reason why lithium ion battery is it's not safe is because it use organic electrolyte. Okay, so that's flammable.
Okay.
Okay, so if you can replace, but if you use water instead, so the high voltage of lithium-ion battery will decompose water first. Okay, and due to the intrinsic instability of water, so that will be that will decompose to hydrogen gas and oxygen gas.
Mm-hmm.
So recently, some members from University of Maryland and also Army Research Lab, they developed methods to make concentrated aqueous electrolyte, so that can actually expand the stability of aqueous electrolyte a lot. Okay, so then they can actually increase the voltage to about 3 volt. Okay, so that's actually very exciting direction to increase the safety of lithium-ion battery. Also, another way to reduce the to enhance the safety of lithium-ion battery is to replace the organic electrolyte with solid materials, for example, like ceramics or polymers. Okay, and recently Samsung actually they published a paper in Nature Energy. They show that they demonstrate a real good performance in solid state batteries, and that battery so won't won't catch fire. Okay, and they show good performance. So these are two very exciting new progress in the field, in my opinion.
Oh wow. I didn't even know about that, but that's a that is very, very exciting even from just listening about it from my perspectives. So for the future, going beyond this research and more research further, what do you want to see and how do you want to see material science and engineering evolve?
I think material science will be there are several directions. One is more automated.
Mm-hmm.
So that means as I mentioned, in many topics of material science, it's difficult to get lots of data. But if it's more automated, then it's possible to get more data. Okay. So and also the combination with computational capability. So artificial intelligence is one direction. The other direction is called the first principle simulation. So that's we just we simulate the system from the atomic level. Okay. So because we know what atoms are there, then we can predict the properties. So and the computational power is stronger and stronger these days, so we can actually predict the performance more and more accurate.
Oh, okay. Yeah,
Okay, and also I think there are also development in the new characterization tools. So now we can see atoms, okay, one by one, and
oh,
also for the CT to look at materials. So like maybe 5 years ago, the resolution is like a 1 micron meter. So that's like the similar size as a cell. Okay, and now people can do about 10 nanometers. So that's actually even much smaller than the COVID-19 virus. So that can help us to better see things.
oh wow. That's very, very that is very, very revolutionary. So going from that, is there anything you want to say about the field of materials engineering to me and to the people watching interested in pursuing material science and engineering?
I think okay. So what I say, this is really an exciting field. Okay, so like so I mean, if you like to create new things or to understand the world, so this is a good discipline to. And also the Columbia Material Science always welcome the uh, I mean students who are interested in this field.
Mm-hmm.
And also, if you want to learn material science, so I would suggest you learn. I mean, uh, in high school, so devote time to like physics, chemistry, or like even mathematics. So that will help you a lot. Yeah.
Yeah.
Mm.
So that for everyone watching, that's what you should do to pursue it. That's definitely what I'm trying to do as well. So any final comments that you want to make before we wrap everything up? And M.S.E, some of the research that you're doing, just overall?
Okay, I think overall, so material science is very exciting. So, but of course, if you work on things, you will find that there are lots of challenges. Okay, but that's actually the exciting and the interesting things. So to solve problem to really make impact to the society. So that's actually should be what uh, people are working on. Yeah.
Oh, wow. So, yeah, that's definitely what I should do and what everyone else who's listening and who wants to pursue it as well. So, while I'm wrapping everything up, thank you, Dr. Yang, for coming on.
Yeah,
Uh,
my pleasure.
we definitely learned a lot.
Mm-hmm.
And yeah, you're always invited back on next time.
Yeah. Okay. Uh-huh. Okay. Stay safe.
You too. Thank you. So that was a very interesting interview with Dr. Yang. I thank him for coming on again. He was an extraordinary guest on STEM Talk with STEM Encounters. And his work spoke to us all. What he does with batteries, energy, and his new ideas in artificial intelligence, the new research that he talked about and brought in, all very, very interesting. His link will be down below. If anyone wants to check him out, read his research, I encourage you to read his research. It's very, very interesting. So, a little wrap up. Remember, as I said before, you can find us STEMencounters.com, our Instagram at STEM_encounters, our YouTube channel, STEM Encounters. Remember, STEM Encounters is almost everywhere. This podcast is on YouTube and Spotify. So, yeah, our next episode will be also very exciting. So, stay tuned for that. And I hope you enjoyed. Thanks.